Let's continue our solution of exercise 8, and today we are going to solve part B. So we already know that we have a metric space x comma d in which this x bar denotes the set of all formal limits of Cauchy sequences in the space x. That means if you have a Cauchy sequence of points in x, then it has a formal limit. X bar is the set of all such formal limits. And if you recall from part A, we also have an equality relation on the set x bar. Now next we are going to define a function like this on x bar times x bar, and we call it d suffix x bar. So it has this as its domain and r as its range. And this is the definition. Because the domain is this, so an input will be an ordered pair of formal limits of Cauchy sequences. Say xn and yn are two Cauchy sequences in x, then these are their formal limits. Dx bar value of this is by definition limit of d of xn comma yn as n approaches infinity. Note carefully that this is a sequence of real numbers. We have to show that this function dx bar is a metric on x bar. We start the solution with two Cauchy sequences xn and yn in our space x, and then we choose any positive real number epsilon. Because these are Cauchy sequences, so we can apply the definition. For this epsilon, there will exist positive integers m1 and m2 such that the distance between xn and xm is at most epsilon divided by 2. Again, you already know that actually we could have written epsilon here, but for something, anticipating something in advance, we have chosen epsilon divided by 2 so that things get adjusted later. For all n and m greater than or equal to m1, and similarly d of yn comma ym is less than or equal to epsilon over 2 as well for all n and m greater than or equal to m2. Why positive integers? That is because the indices of these sequences start from 1. They vary over the set of positive integers. Then for all n and m greater than or equal to the maximum of m1 and m2, say we consider the distance between xn and yn, suppose, and let's see what we get. By triangle inequality, this is less than or equal to d of xn comma xm plus d of xm comma ym plus d of ym comma yn. So actually we have applied triangle inequality 2 times here. Now because our n and m are both greater than or equal to this max value, so they both are greater than or equal to m1 as well as m2. So this inequality as well as this one are with us. Okay, so they are both with us. That is why this is less than or equal to epsilon over 2 and this one is less than or equal to epsilon over 2 as well. The middle term of course stays. Note carefully that in this first term we have the terms of the sequence xn, whereas here we have the terms of our sequence yn. And then you add these two things, get epsilon plus d of xm comma ym. This is less than or equal to this epsilon plus this. So that means this minus this is less than or equal to epsilon. And this is happening for all n and m greater than or equal to this max value. Similarly, we have this as well, d of xm comma ym minus d of xn comma yn less than or equal to epsilon for all n and m greater than or equal to this max value. How? See, whatever calculation we did here, starting with this, we can do a similar calculation starting with this one and following similar steps. That will get us this inequality. So both this difference as well as its negative are less than or equal to epsilon. So the absolute value of this difference is also less than or equal to epsilon for all n and m greater than or equal to this max value. But then what does that mean? It just means that this sequence dxn comma yn of real numbers is a Cauchy sequence in R, and that means it's a sequence of real numbers. Because this condition just tells us exactly that. But we already know from a previous result that every Cauchy sequence of real numbers is convergent, and that result is theorem 6,418. So by that, this is convergent. It has a limit which is a real number, and at the same time that limit is non-negative as well. That is because each term in this sequence is a non-negative real number. That's why by the comparison principle, if you recall, the limit will also be non-negative. So what are we getting out of these things? This is what we get out of this discussion. What have we done? We have taken two sequences, Cauchy sequences of points in x, xn and yn. So these are their formal limits. So that means they are elements in x bar or points in x bar. And by the definition of this function dx bar of this comma this is the ordinary limit of this sequence of real numbers dxn comma yn. So this shows that this sequence converges, so that means this limit exists. It's a real number, and additionally it's a non-negative real number. So that is why it belongs to this closed ray. And this is what we expect from a function that we are going to show is a metric, right? This is supposed to be the distance between these two formal limits. So obviously it should first of all be real, and the second thing is that it should be non-negative. So that we now have, but still there is one more thing. What about the uniqueness of this distance? If instead of this Cauchy sequence xn, if you choose a different Cauchy sequence whose formal limit is also this, then will that choice affect this distance? If so, then this function is not well defined. So the next thing we will now show is that that does not really affect this distance. I have put this part within these dashed lines to indicate that this is not a part of the formal solution. It's like a checkpoint. Here we have checked whatever we have achieved so far, and now we can move on. And for that, we have next taken a Cauchy sequence xn prime in x whose formal limit equals the formal limit of xn. Now if in place of this we use this one here, will that affect this? So let capital L1 be the limit of d of xn comma yn as n approaches infinity, and L2 be the limit of d of xn prime comma yn as n approaches infinity. We want to show that L1 and L2 are equal, but suppose they are not equal. If we can show that something goes wrong, then that means they should be equal. Now choose any positive epsilon again. Then for this epsilon, there exist positive integers k1, k2 and k3 such that d of xn prime comma xn is at most epsilon divided by 3. This time we tweak the value a little bit again for something. For all n greater than or equal to k1. Why should such a k1 exist? That is because the Cauchy sequences xn and xn prime have the same formal limit. And that means you go back to part A and see the definition of equality of formal limits. The sequences are related like this. That's why we have such a k1. And additionally, the absolute value of d of xn comma yn minus L1 is less than or equal to epsilon over 3 for all n greater than or equal to k2. This comes simply from the fact that this sequence of real numbers converges to L1. And similarly, because this one converges to L2, this difference, such a difference is less than or equal to epsilon over 3 for all n greater than or equal to k3. So we also have a k3. Now we choose an integer n which is greater than or equal to the max value of k1, k2 and k3. And let's consider d of xn comma yn. By ordinary triangle inequality, this is less than or equal to d of xn comma xn prime plus d of xn prime comma yn. And then you can subtract this from both sides, obtaining this d of xn comma yn minus d of xn prime comma yn is less than or equal to d of xn comma xn prime, which however is less than or equal to epsilon divided by 3. Why? See, this happens only when n is greater than or equal to k1. Because n is anyway greater than or equal to the max value of these things, so automatically n is also greater than or equal to k1. That is why we have this. Similarly, we also have this d of xn prime comma yn minus d of xn comma yn is less than or equal to epsilon over 3 for this type of n. So whatever you did here, instead of starting with this one, you start with this one. Okay, you already know now because we did something similar just now. So that is why this difference is less than or equal to epsilon over 3 and its negative is also less than or equal to epsilon over 3. So its absolute value is at most epsilon over 3 where n satisfies this inequality. So for any such n, next we consider this quantity which initially does not have any n, the absolute value of L1 minus L2. By two applications of triangle inequality, this is less than or equal to the absolute value of L1 minus d of xn comma yn plus the absolute value of d of xn comma yn minus d of xn prime comma yn plus the absolute value of d of xn prime comma yn minus L2. Now this is less than or equal to epsilon over 3 that we have shown just now. And this are also less than or equal to epsilon over 3. Why? For this to be less than or equal to epsilon over 3, we need, I think if I am remembering correctly, we need n to be greater than or equal to k2, which however is true because of this thing. Similarly, because n is greater than or equal to k3, this is also less than or equal to epsilon over 3. And that's how we find that mod L1 minus L2 is less than or equal to epsilon. Note carefully that although we used n, but ultimately this is a fact which is independent of n. Since epsilon is an arbitrary positive integer and L1 and L2 according to our supposition are different, so we can choose this specific value of epsilon, 1/2 of mod L1 minus L2. This ensures that L1 minus L2 is non-zero, and because we are taking modulus also, this becomes positive. And for this epsilon also, this should be true. That means this should be less than or equal to 1/2 of itself, which however is false, because this is a positive real number. You can cancel it from both sides, obtaining the wrong inequality 1 is less than or equal to 1 over 2. And this absurdity stems from our supposition, which must thus be false. So L1 has to be equal to L2. So L1 is equal to L2. Whatever I said here just now, you can write those things. Okay, I am not going to write them again. And now only we can conclude that thus dx bar is well defined. Not only will you get a non-negative real number as the output, as an output for this function whenever you take two formal limits, but the Cauchy sequences that lie behind those formal limits, it does not matter if they differ from some other Cauchy sequence. If the formal limits are equal, the ultimate result will be unaffected. That is why this is a legitimate function. And now we can go for showing that this is really a metric. So let's verify the axioms one after another. Let's take the first one. For any formal limit, limit of xn, that means behind this formal limit, we have a Cauchy sequence of points xn in our original space x. So this formal limit belongs to x bar. For any such point in x bar, what is the distance between the point and itself? Although we should not say distance, but because anyway we are going to show that this is a metric, so I am saying like that. By definition, this is the limit of this sequence of real numbers, d of xn comma xn. Because the original d, which is a metric on x, is a metric, so this is equal to 0. That means here we are looking at the constant sequence of real numbers where all the terms are 0, and that of course converges to 0. So the distance of one point and itself, between one point and itself, is 0. This is what we expect from a metric. Number 2, let this and this be two formal limits such that the distance between them is 0. Then by the definition of this function, limit of d of xn comma yn is 0. But if you go back and see the definition of equality of formal limits, it is precisely when this happens that we say that these two formal limits are equal. You may get a little confused about this number 2, second condition in the definition of a metric space, because in the text I think it's given like this: if two points are different, then the distance between them is positive. Actually, we have proved just that, not exactly that, but it's contrapositive. We have showed that if the distance is 0, then the points are same. What does that mean? It also means that if the points are not same, then the distance is not 0. But the distance, as we already saw there, is either 0 or positive. So that means in that case distance is positive. So this is really condition 2 that we have proved. Next, number 3, symmetry. Again we take two formal limits, and this time we just straight away consider their distance in this order, which by definition is this. But because this d is itself a metric and has its own symmetry, d of xn comma yn is just d of yn comma xn. So this limit again becomes this by the definition of dx bar. So it does not matter in what order you choose the points, the distance stays the same. The distance of this one from this one is the same as the distance of this one from this one. And finally, number 4, triangle inequality. For that we have chosen 3 Cauchy sequences in X. We could have straight away taken formal limits also, but here this becomes necessary. So for any positive integer n, we have triangle inequality for the metric d. D is already a metric which is with us. D of xn comma zn is less than or equal to d of xn comma yn plus d of yn comma zn. Now what are we going to get from this? This is what we get: dx bar value of limit of xn comma limit of zn, which of course is equal to limit of d of xn comma zn, but that is less than or equal to limit of d of xn comma yn plus limit of d of yn comma zn. How are we getting this step? See, first of all, you are looking at 3 sequences of real numbers here, all of which are convergent, that we proved in the beginning itself. So because this one and this one are convergent, their sum is also convergent by one of the properties, that means algebra of limits. So this sequence is convergent, this sequence is also convergent, and they are related by this inequality. So we have used the comparison principle. That way the limit of this will be less than or equal to the limit of this, which however by algebra of limits is equal to limit of this plus limit of this. That's how we are getting it. This however is dx bar of limit of xn comma limit of yn, and this one is dx bar of limit of yn comma limit of zn. Is this not the triangle inequality for dx bar? Yes, it is. So finally we have shown all the things, and now we can write the conclusion that hence dx bar is a legitimate metric on x bar, and there the solution ends.